Hi, everyone. So I'm Cécile Deligny. I'm a postdoc at the Swedish Museum of Natural History in Stockholm. And yeah, today I'm going to talk to you about a recent study that we did. We should be able to submit it in a couple of weeks. And it's about an Apollo 12 basalt. So here you have a map of the moon, and then you can see here the landing site of the Apollo 12 mission next to the Copernicus and the Kepler craters. So as you may know, the Apollo mission permitted to collect three different groups of basalts. So olivine, pigeonite, and ilmenite basalts. And among all of these collected basalt, there is a peculiar one. So it's the 12032. And what is really interesting about this basalt, it's really rich in thorium compared to other Apollo 12 basalts. I'm going to talk about that in the next slides, but there is also some difference in the chemistry between all of these basalts. And also it was suggested before that it may come from a different region than the landing sites. And here you have a picture of the sample, and it's only 41.2 milligrams, which is really, really small. So now we can talk about chemistry. So what is really important with these basalts is that mineral and trace element chemistry is really different from other Apollo 12 basalts. So here you have a diagram with the thorium concentration as a function of the iron concentration. So I don't know if you can see the color here, but you have the different Apollo mission here, and also you have Lunar sample and Chang'e 5 mission. And here is so our sample, and as you can see, it's the composition and more specifically, the concentration of thorium is really different from other Apollo 12 basalts, and also it's different from Chang'e 5 basalts, for example. And when we look at the iron content, we can see that it's pretty similar to other Apollo 12 basalts, but really different from Crepes basalt, for example. Also, there is a study of Barra et al. 2006, and they did argon-argon dating. And they found out that the age of crystallization of the sample should be 2.3 billion years. And they also state that probably the gassing occurred around 700 million years. So here it's the sample that we were able to analyze. So this is a false color map of with the SEM that we did. And you can see with the different colors that the sample is mostly composed of olivine, pyroxene, ilmenite, plagioclase. And there is also a few minor phases. But what we are really interested here to do some datation is the mesostasis. So here you have two backscatter electron images of the sample, two different zoom on different parts of the sample. And I don't know if you can see here, but you have some mesostasis here and here also. And we are really interested about the mesostasis because lead is in incompatible element. So during crystallization, fractional crystallization, the lead will remain in the residual melt. So all of these different phases in the mesostasis will be enriched in lead compared to olivine or plagioclase, for example. And within this mesostasis, we can see that there is a small grain of silica, pyroxene, potassium-rich feldspar, etc. So what we did here is we measure the lead isotope by SIMS to be able to date this sample, and then we can compare it with different basalts and see if there is a link with another groups. So as Renaud and Josh mentioned, so we did SIMS at the museum in Stockholm. So it's in situ analysis, and we do that on a thin or thick section of samples. So you don't need to do chemistry for those measurements, and you can measure the different minerals that you want. You just need to adapt the primary beam, so the spot size. And yeah, so we measure lead isotopes, and here you have a picture of the samples, and you can see the black dots. It's all the measurement that we did in that sample. So I'm not gonna get into too much details here, but as it was mentioned before, so for lead measurements, so we measure the 207-206 ratio as a function of the 204-206 ratio. So Josh mentioned that we can have some terrestrial contamination that you can see here with the yellow dot. And here it's all the measurement of the different phases, for example, phosphates, potassium feldspar, sulfides, etc. And of course, you can have some contamination, so you need to discard all these points. And then you can have the isochrone, and you can determine the age of crystallization of your sample. So here is the results for the 12032 samples. So again, here you have the 207-206 ratio as a function of the 204-206 lead ratio. And we were able to measure the lead isotope in the mesostasis, pyroxene, plagioclase. And also when I put mixing, it's because there is a lot of different really tiny minerals, and I can decipher between if it's only like a zircon or if it's just a feldspar. So I show that as a mixing. And we were able to tell that the crystallization age of the sample is 2.4 billion years. So now we can compare both the chemistry and also the age of formation of the sample with other basalts to understand its origin, its provenance. So first, of course, we will compare it to other Apollo 12 basalts. So usually Apollo 12 basalts have a crystallization age of 3.1 to 3.3 billion years, and our sample is 3.4, so it's older. And also, as I showed you before, for the thorium and also for minor and trace elements, this sample is really different from all the Apollo 12 basalts, so the different suites, so pigeonite, olivine, and ilmenite. So we consider that this sample is really not comparable to other Apollo 12 basalts that we know. Then we can compare it also with Chang'e 5 mission, because this mission is, I mean, it's far, but it's not that far from the Apollo 12 landing site. And also there is some similarities for the trace elements contents between the Chang'e 5 basalts and our sample. But unfortunately, the crystallization age of Chang'e 5 basalt, it's much more younger, around 2 billion years compared to our samples. So we consider that they are not related. And finally, we can compare it with the Crete basalts because they are known to be enriched in thorium, such as our sample. So our sample contains 7 ppm of thorium. But again, when we compare, for example, the iron content, the aluminum content with the Crete basalt, it's quite different. And again, the crystallization age of Crete basalt, it's around 3.8 billion years, which is much older than our sample. So again, we said that this sample is not related with known Crete basalts. So now the question is, where is this sample coming from? And if we can use the composition, the age, and remote sensing data to understand its origins. So as you know, impact event played a huge role, and we'll eject some materials and distribute it on the surface of the moon. And as I mentioned before, so from a previous paper, they did organ dating, and they found out that there is like a disturbance between 500 and 700 million years. So we consider that this might be due to an impact. So now if we look at the map, the different maps. So here again, I show you the first map that it was on my first slides. And here you have a chemical map with the titanium content from 2 to 9 ppm. And as you can see in the Kepler region, we can see that there is a lot of different area with thorium content between 3 and 6 and 7 ppm, which is exactly what we have in our sample, 7 ppm of thorium. Also, we can see with the crater counting that on the west and east part of the Kepler crater, there is basalts with age of formation between 3 and 3.6 billion years, which is the range of our sample. So we consider that this sample might be ejected during the formation of the Kepler crater, and then it was collected on the landing site of the Apollo 12 mission. So yeah, that's our conclusion that this sample is probably coming from this region located near the Kepler crater. Thank you.
Have any questions? We heard in the talks before about mu value. Is that mu value for that sample different to other Apollo 12 samples?